The law for logarithms of powers says the following. If you have the log base a of m to the power of p, then, and this is really one of the most powerful things that you will learn about logs and why logs are so useful, then I can actually express that. If you look at where my mouse is pointing right now, I take the log of a power, m to the power of p, this thing here, is called a power, right? A power has a base and an exponent. So m to the power of p is a power. I can take the p from the power, the exponent, and put that in front of the log. So that's exactly what you see happening here. So the exponent becomes like a coefficient, right? So it's the same thing as p log base a of m as long as m is greater than 0. In other words, you can't take the log of a negative number. I should have mentioned this yesterday. It's being recorded. Yes, Jeremy. So you can't take the log of a negative number. So that's one of the restrictions on logs. So they keep making the restriction that the thing that you're taking the log of has to be positive, and that p must be a real number, right? So none of these square roots of -1, that kind of thing. The log of a power equals the exponent of the power times the log of the base of the power. That's what this law of logarithms of powers says, basically. This person is trying to gain entry again. I'm going to have to deny that person. Not sure who that is, but can't admit anybody outside of the board. Okay, so what does that mean for a question like this? Well, it's very simple. It means if I was asked to find the base 3 log of 9 to the power of 4, then I can write that as 4 the log base 3 of 9. All I've done is I've taken the 4 and put it in front of the log. That's a perfectly legitimate mathematical statement to write. So, of course, we did all this stuff about logs yesterday. We know the base 3 log of 9 is, hopefully everybody knows this, is 2, because the exponent on 3 that gives you 9 is 2. So the answer for this is 8. Okay? It's really that simple. The same thing would work with the second one, the log base 2 of 8 to the power of 5. So I'm going to say that I can write that as 5 times the log base 2 of 8, which means that that's the same thing as 5 times, well, the log base 2 of 8 is 3. So the answer is 15. So it's a very useful concept to learn and to apply. All right. So this is the same as the 2 before, a and b, where I'm going to put the 2 in the front and say the log. Now, there's no base stated here, so we're going to just stick a little 10 in there to remind you that when there is no base stated, it means that it's a base 10 log. And then 0.001. And I remind you what I told you my primary school teacher taught me, that if I want to take that and make that into a fraction, it would be 1 for the decimal point, sorry, 0.001, 1 for the decimal point, and then 3 zeros after that. So it's really the same thing as the log of 1,000. So it's 2 times the log of 1 over 10 to the power of 3. All right, that's what 1,000 is. And therefore, that's 2 times the log of, hopefully I don't have to go through all the steps, minus 3. Right? 1 over 10 to the power of 3 is the same thing as 10 to the minus 3. So that would be, actually, I'm saying that wrong. It's not the log of minus 3. It's 2 times minus 3, because the log of this is minus 3. So let me just erase this part here and say that this is 2 times simply minus 3, which is, of course, minus 6. So the log of 0.001 squared is minus 6. Okay? All right, how about this one? The log base 5 of the square root of 125. Uh-oh. Can anybody suggest how I might make this look more presentable? Is there a way that we can make this more presentable? Jeremy, go ahead, please. Mm-hmm. Mm-hmm. Yeah, good, but you're going too fast for us. So here's what we're going to do first. We're going to do this. We're going to say the log base 5 of 125 and raise that to the power of a half, because that means the same thing as what we said yesterday. Means the same thing as the square root of 125. Okay, so because the denominator here of 2 means I'm taking the second root of 125 and raising that to the power of 1. I guess you can look at it that way. No, I'm just going to continue. So I understand what you're saying, and you're right about your answer, but I want to go with the power law, which means I don't want to put that half in the front of this. It's a half of the log base 5 of 125. And if you think about it, the log base 5 of 125 would be 3, right? Because it is 5 to the power of 3 that gives you 125. So, of course, at the end of the day, it's the answer that we just got from Jeremy, which is 3 over 2. It's another route, the way that Jeremy did it, of getting the same answer, right? So 3 over 2 is the result of the log base 5 of the square root of 125. 3 over 2 makes perfect sense. Okay, well, if that kind of was okay, I'm going to move along and show you now how we can apply that to what's called a change of base formula. Let me go through this, in fact, step by step. So let me take it one step at a time. Let me start by saying that if I have something in log form, such as x equals the log base b of m, right? Something we said yesterday is what we call the log format. Then I can take that, excuse me, and put it into exponential form by saying b to the power of x equals m. That's the exponential form of the first statement, which is the log form, right? Hope everybody remembers that. All right, so this is the log form, this is the exponential form. All right, now, what if we took that exponential form and took the log of the two sides of that? All right, what if we, so it's not like saying we're putting it back into log form, we're just taking the operation of doing the same thing on one side that we do on the other, which is to take the log of the two sides. So I took the log of the left-hand side and took the log of the right-hand side. The log of b to the power of x, and when I say log here, I mean the base 10 log, by the way. The log of b to the power of x is equal to the log of n by just taking the log left, log of the right. According to what we said a few minutes ago, I can rewrite this left-hand side with the x in the front. X log b is equal to log n. I'm just applying that power law of logs that we just talked about. So that's why I can write that. Okay. So I can now isolate my x then in that case. So that x would be equal to log base m, sorry, log of m over log of b. That's what my x is. If I put the x in the front, and that's the whole point about this power law, it does allow us to isolate that exponent. And you'll find that when you're trying to solve an equation that has an exponent as a variable, the power law of logs is powerful. And I'm saying that with pun intended. It's very powerful in helping us to do that. So that means that the x that we had in the first place, this x here, which is equal to the log base b of m, is also equal to the log of m divided by the log of b, which means since x is equal to this and x is also equal to this, it means the following, that the log base b of m is equal to the log of m divided by the log of b. We have all of these different formulas on the test. You should certainly know, yes, these formulas for the test, right? Am I going to spell it out for you? Well, maybe, we'll see. But it's a very simple concept, and that's why I'd like you to understand the process of getting it so that you can apply it. So for any log base b of m, remember all the logs that we've looked at so far, right, are stuff that we can easily figure out. So when I asked you, for instance, yesterday for the log base 3 of, let's say, for instance, 27, where everybody knew it was 3, because 3 to the power 3 gives you 27. The log base 2 of 8, we had this morning already, is equal to 3 as well, because 2 to the power 3 is equal to 8. But what if, what if I suddenly did this and said, what's the log base 4 of 9? Now you're kind of stuck, right? Now you're not exactly sure where to go with it, because I can't think off the top of my head of what number I can raise 4 to that gives me 9. What exponent, because a log is an exponent, I've said that a couple of times, right? What exponent can I put on this base of 4 that gives me, I don't know what it is. I just don't know. But according to this line above it, it says that if I wanted to find the log base b of m, or in this case, the log base 4 of 9, then all I have to do is to take the log of 9 and divide it by the log of 4. That's what's called change of base, right? Formula allows us to do. So the base initially was a base 4, but we said, okay, why don't we just do a log of a 9 over the log of 4? Now, you might be asking me, what base am I using for this log here? What base am I using for this log here? It doesn't matter. As long as, and here's the important point, as long as the base that you're using on top is the same base that you're using on the bottom. So if I use a base 10 log on top and you have a base 10 log here in your calculator, then I have to use a base 10 log on the bottom as well. If I use the ln key, which is that other key I've been telling about, the ln or the natural log key, then it means I have to find the natural log of 9 over the natural log of 4, and I still get the same answer. So just default log would work. Yes, Jeremy. So just using log itself. In fact, here's what we'll do. Grab your calculators, everybody, and let's do this both ways. I want to find the base 4 log of 9. This is my goal right now. So base 4 log of 9. Let's do it two different ways. Let's use the base 10 key for both. And since you all have your calculators, can you tell me what that number is, please? Right? It's gonna be a decimal of some kind. I don't know what it is, but I just made up log base 4 of 9 on the fly. Give me that decimal to 2 decimal places. Or, well, I got 3, that's fine. 1.585. Thank you very much, Isaac. 1.585. Now, let's do this using the ln key. So find the ln. So again, we're trying to find, let me just remind you what we're trying to do here. We're trying to find the log, we're trying to find the log base 4 of 9. So I'm going to say, instead of using base 10, I want to be fancy, okay? I'm going to go ahead, and thank you, by the way, Travis and Harish and Emily and Jeremy, all of you where have come to the 1.585. I mean, I just took Isaac's answer. He gave me 3 decimal places. That's okay. Now try this. Try the ln, use the ln key this time, of 9 over the ln, what they call ln, the natural log, that's the way they refer to it, over the ln of 4. All right, what answer are you getting this time? All right, using ln, same answer. Are we agreeing with that? Can we all confirm that we're getting the same answer, the same 1.585, exactly the same answer? There's no difference, right? So assuming that we got the right number initially from Isaac and from Jeremy and from Karis and everybody else, 1.585. And I'm going to say, as long as you use the same base, okay? It has to be the same base. So now we have a way that we can find the log for any base. Now, I already know that some of you have calculators. Should it be right or left of log? Should be to the right or left of the log, Isaac. Oh, there's a question. Can't find the button. Oh, yeah, it's usually, right? Usually, I mean, not all calculators are the same, but it's usually right beside the regular log key, right? Usually that's where it is, but it does depend on your calculator. All right. All right, so Isaac seems to have found it. It's a Casio FX3. Oh, those are great calculators, by the way. Great, great calculators. I love Casios. I guess you must have figured that out by now. I love Casios. Anyway, All right. And I don't have any shares in the company, so that's not the reason. I just have a lot of faith in them. I own, I think, two of them at this point in time. Anyway, let me move on. Let me move on. So now we can, and by the way, this works for the stuff that we already knew, right? So if I said to you, let's try this right now. If I said to you, what is the log base 4 of 16? Well, we all know it's 2, right? We all know that that's equal to 2, right? I don't need a calculator for that, or hopefully you should need a calculator for that. But now I can also figure this out by taking the log of 16 and dividing it by the log of 4. Try that for yourself right now. And again, whether you want to use the ln key or you want to use the log key, as long as it's the same for top and the bottom, you still get 2, right? We already knew it was 2 because you know that 4 raised to the power of 2 gives us 16. But here is another way that if we were struggling to figure it out, we would do with the calculator. All right? All right. So we now know how we can find the log in any base, right? And again, I should point out that a lot of you, let me see if my virtual calculator on here has that key that gives you the log in any base. Let's bring that up now. Hold on one second. It does, yeah. Some of you might see that key on your calculator that allows you to find the log in any base. I'd show it to you on my screen. Log has a base of 10 with having a base E or 2.71828. Let me see if I can figure out what Jeremy is saying here now. Log is a base of 10, that's correct. But the E is the base that you use for ln, and that base is 2.71828, and then it goes on from there. He's answering as that question. Oh, okay. All right, got it. All right, I'm not following the chat as closely as I should. Sorry about that, folks. Let me move along. All right, so go ahead now, and everybody evaluate for me the log base 3 of 23 and the log base 6 of 20 to 3 decimal places. All right, so go ahead with the first one. The log base 3 of 23 using the same method we just learned, and also the log base 6 of 20. Let's start with the log base 3 of 23. All right, who has an answer for me on that? Give me 3 decimal places as it says. Correctly rounded, please. Make sure you round it correctly. All right, so I'm getting 2.854 from Isaac, and the same thing from Jeremy. 2.854. All right, and give me the log base 6 of 20 now. What's the log base 6 of 20? I'm going to ask another question. Well, I'm hearing it's 1.672. Okay, so let me ask you a question then. Let me just see if people are really following along with all of this logic here. What if, let me go back to A, I were to take the 3 and raise that to the power of 2.854. What do you expect? Don't do it on a calculator. Just ask just how much you think I'm going to get. If I took that 3 and raised it to the power of 2.854, what do you think I would get if I did that? Don't put on the calculator yet. Just answer my question. All right. Harish says 23, something between 9 and 27. Interesting, Jeremiah says. I'm going to agree with Harish on this. It's going to be exactly, well, you know what? I'm going to say exactly because this was rounded in the first place. It should be approximately equal to 23. It's not going to be exactly 23. It's going to be, 23.001 or 22.999 because we had to round the original value of 2.854. Okay, you got 22.998. There you go. There you go. Right. And the same thing would happen here. If I were to raise 6 to the power of 1.672, shouldn't we expect to get 1.00? Whoa, where is Travis getting that from? What is that? Well, yeah, should be getting approximately 20. Travis, I'm trying to understand what you just put in there. The 1.001746. What does that signify? I'm not sure I follow what that is all about. The actual calculation. Oh, okay, okay, all right, yeah. But for me, I would just let the calculator do all the work. I wouldn't write down the intermediate answer. I just find the log of 20 divided by the log of 6 and then press the equal sign, right? That's what I would do. And if you did that and you, oh, I see what you're saying. I see what you're saying. If you use the actual number that you got, I got you. Excuse me. If you use the actual number you got, then you would get back to 23. If you use a number that the calculator worked out without rounding it and just store that in memory or something like that, and then used the base and raised that base to that number, you'd get exactly that number. Yes, you're absolutely right about that. Okay, so I just thought I'd make that point. Now, let us see how powerful this concept of the power law of logs is as it relates to compound interest. So this formula basically tells you how much money, that's what the A represents, will be in your account if you put in this amount of principal. Principal is the starting amount, right? Getting this amount of interest, the I is the interest rate, for this amount of time, and represents the period of time that you are investing your money. Okay? All right. So if you bear that in mind, and hopefully this is kind of coming back to you now as we go through this, we can actually set up this information into this formula right now. So you're starting off with $10,000 and you're trying to get this up to $15,000 and you're earning 5% compounded annually. Okay, it should be a mandatory class. So I agree with you. I completely agree with you. Did I ever bring, before, a little bit aside here again, did I ever, I think I started the class with this. I don't remember if I did or not. On the very first day, did I show you the salmon in the flyers? Did I do that with this class? I'm trying to remember if I did that. I did do that, yes. Okay. Because stuff like that, I think, is just practical, everyday, information that, or skills, I should say, that everybody needs to have. Anyway, let's get back to this. Okay. Enough about money and me. Let's get back to this. So the amount of money that you're trying to get to is the $15,000. So that's your A, right? And you started off with $10,000. Yes, yes, counted a fish. Yes, yes. And so I'm going to leave that behind now, though. We started off with $10,000. So that's my P. And my interest rate is 5%. So it's 1 plus, but I have to express that 5% as a decimal. So 0.05 to the power of n. Well, guess what? That's the thing we don't know. We don't know how long it's going to take. I'm sitting out my financial planner. I'm telling him I have $10,000 and I want to get to $15,000 because there's that shiny new, I don't know, something I wanted to buy. And I need to know at a 5% interest rate, Mr. Financial Planner, numbers guy, how long is it going to take for me to get to that $15,000? That's the question that I'm posing to Mr. Financial Guru sitting in front of me across the table. So he pulls out his calculator because he was in Mr. Kamak's finance class and he said, oh, I can do this. What is the first thing you think he's going to do at this point? I'm trying to solve for n. Can anybody give me some strategies, some techniques, some steps that I could maybe follow to solve for n? Any ideas to solve for n? Divide both sides by 10,000. That's actually a pretty good step. So let's do that. So 15,000 divided by 10,000 is equal to, I'm just going to call this 1.05 now because 1 plus 0.05 is 1.05 to the power of n. Okay. So, and while doing that, I add 1 to 0.0. Yes, it's not 0.005, though it's 0.05. Yeah, right. Okay. So there we go. Well, this part's not hard. That's just 1.5. Right? I don't need a calculator for that, really. Is equal to 1.05 to the power of n. I don't really need that bracket there anymore. So now we need to solve for n, is the question. Okay, so how do I do that? I mean, I could do trial and error. I could try different numbers, try 1, try 2, try 1.5, try 2. In other words, I could play around with this for a long time until I came pretty close. But look at what Noah just said. Noah says take the log of the two sides. That's exactly what we're going to do. So we're going to say that the log of 1.5 is equal to the log of 1.05 to the power of n. I think that's an excellent idea. Okay. And let's see what else we're saying, Jeremy. We can try and use the log. Yeah, okay, okay. What does that mean? What is my next line going to say, Jeremy, then, if that's the case? What am I going to write on my next line? I want to follow this in as kind of a step-by-step approach. If the log of, so remember, all I've done is I take the log of the two sides, right? The log of the left equals the log of the right, which is perfectly legitimate. Move the n to the front of the log. Okay, good. So it means that n log 1.05 is equal to the log of 1.5. All right. All right, we're going to put this aside for now. We'll get this out of the way here. We'll come back to that. All right. The log of 1.5 is equal to n log 1.05. Then divide both sides by, oh, okay, I think I can do that. So you're saying divide both sides by the log of 1.05. All right, okay. So that would mean I would end up with just n on this side. So n is equal to the log of 1.5 divided by the log of 1.05. Okay, and then solve for n. All right, okay, that seems like a pretty good strategy. And can I get you to not just one person, can I get everybody to 8.31, I'm hearing? That's approximate. I know you had to round that a bit. And Janai is getting the same thing. Isaac is on the board with that as well, right? What units does it make sense for me to put this in? And I want a statement of some kind. What units make sense here? All right, this was a word problem, and I need to figure out it would be years, absolutely. So I'm going to say that it would take always have to put a statement, a therefore statement. It would take 8.31 years to reach $15,000. Okay, so I can now confidently think about this and say, okay, Mr. Financial Plan, I'm going to give this money to you, and in 8.31 years, I'm going to come back and I'm going to expect a check for $15,000. All right. Now, obviously, if the interest rate was lower, it would take longer. All it's going to take you to double your money. So now you got greedy and you thought, 8.31 years. I won't be that old in 8.31 years. I can wait for that. But what if I got greedy and said, I want to double my money now? Right? And I also want to show you a shortcut way that financial planners use. In a second, I'll show that to you to figure out what that number is. But how long does it take to double your money at the same interest rate? Can you help me to walk through how that might look? Right? How can I double my money? Right? Is there a way that I can come up with that number? You set it to $20,000, Harry says. Okay. So let me see if that makes sense. I started off with $10,000, and now I'm saying I want to double my money. So instead of it being 15, right? This person is thinking, I want to go beyond 50. I want to get to 20. And you're right, that's doubling your money. So we'll do the same calculation again. So I'm going to say $20,000 equals $10,000, 1.05, same interest rate to the power of n. I'm going to get you to work that out for me, please. Then I'm going to tell you a shortcut that financial planners use a lot when they're trying to 100% return. Yes, 100. Well, you're doubling your money, so I guess you could got 100% return. Yes. All right. So can you work that out for me right now? Tell me what n is. Go through all the steps and tell me what n is equal to. Then I'll tell you what the shortcut is after that. So everybody go ahead and get your calculators out. Go through all the steps we just went through with this calculation, right? I'll just scroll up again to give you an idea what that looked like, and work out your value of n. I'll give it a shortcut later on. You think you got it? Okay, hold it for me for now, Jerry. Let me give everybody else a chance to come up with a number. Then I'll tell you what the shortcut is. Hang on. Okay, so Joel. Thank you, Jeremy. Thank you, Travis. You got it as well. Let me hear what Joel thinks. Joel, you did you work through the calculation? Did you go through that calculation, everybody else? Joel? Where's Joel? I don't like having to call people out and I can't hear from them. Okay, Joel, can you give me your answer for that, please? We have Jeremy and Travis standing by with what they think the answer is, and they will tell us whether they got the same thing or not. Do you have your answer, Joel? I'm assuming you're not just sitting there, but you're actually working along with us. So what's your answer? The idea was for you not to just wait for somebody else to work it out, but for you to work it out for yourself. So over to you, Joel. Joel, are you working this out? Okay, all right. And I hope if I asked anybody else that they would also have their answer. I know Travis and Jeremy said that they have theirs, but you should also have yours. Right? Shouldn't be that when I call on you is the time that you decide to work on it. That's why you're in class. You're expected to be working along with me as I go through these questions. While Joel is working on that, I'm going to write an expression down and I'll explain what that expression means. The rule of 72. Or does anybody already know what this rule of 72 is? Okay, your answer is 1.905. Wow, okay, I'll write that down. All right, so Jeremy, Travis, weigh in for me, please. Is that what you got? Not even close. Not even close. All right, Jeremy got 14.21. Travis got 14. What did other people get? All right, did anybody else get 1.95 or did you get the same thing that, okay, Emily and, okay. So Joel, I'm going to suggest that you look back through what you saw me do a few minutes ago. Hopefully you were paying attention and make sure that you get the answer that they're getting. And I'm going to tell you why I know that answer is probably right. So I'm going to have to put an X through this and take the answer of 14 point, is that 14.2? And that's of course years again. The reason I know that that answer is probably right, I haven't worked it out yet, is because the rule of 72 says, and this is what financial planners use all the time, if you want to know how long it's going to take you to double your money, then divide the amount of, divide 72 by the rate of interest. It's a rough, it doesn't exactly, my bad, I had a mistake in it, 14 point, yeah. It doesn't exactly, it's not as accurate as doing logs, but it's a rough approximation. It does work. 72 divided by the interest rate. In this case, that would work out to be 14.4 because it's 5%. Don't put it as a decimal, by the way. Just use a number as it is, 14.4. And what financial planners will say is that that's not exact, and I need logs to be more precise. But if I just want to give you a rough idea, I could use this. I could use this method. Okay, let me show you again what I mean by that. So in this case, it would have been 14.4. I want you now to do the same thing. I'm going to use a rule of 72 and say that if this was a 2, let me give you a rate of interest that's more realistic. Let's say it was a 2%, or let's use 2%. So if it was a 2% interest rate and I want to double my money, then 72 divided by 2, of course, is equal to 36. Let's do the same thing with logs, though. So change your formula, and I'll show you how to change the formula. It's still going to be $20,000 is equal to $10,000. And by the way, you'll notice that it's really always going to be equal to 2, right? The 1.02 to the power of n is always going to be equal to 2, because if I'm doubling my money, then whatever number I have on the left-hand side here is always going to be half of what is on the right-hand side. So 1.02 to the power of n. Work that out, and you should get an answer that's very close to 36. It's not going to be exactly 36, but do the same thing that we just did using 1.02 for 2%. And let's see what you're getting this time. Right? Let's see what you're getting this time. Wait, can you quickly explain that again? Okay. So the rule of 72 says, if I want to know how long it takes me to double my money, I just simply divide 72 by the interest rate that you're offering, right? So the interest rate that you're offering in this case for this question was 5%. So I'm saying it would work out to be about 14.4. Well, what if it was an interest rate of 2%? Well, what the rule of 72 would tell me that they'd be equal to 36. But I'm saying let's do this with logs. So let's take the 20,000, set it equal to 10,000, but use 2% this time. So 1 plus 0.02. So 1.02 to the power of n. So this is what I'm asking you to solve. And I have one answer already coming from Travis, who says it's 35.0. So n, I'm assuming everybody else got something close to that as well, 35.0. So it's not as precise as logs. It just isn't. But it's rough. It's going to be within 1 or 2 years of doing the log calculation. So that's what they call the rule of 72. So if I have a product and I'm taking the log base b of that product, then I can also write that as a log base b of the m plus the log base b of the n, as long as the base is positive and that the base is not equal to 1 as well. The m and the n must also be positive. So again, let me repeat this. I cannot take the log of a negative number. If you try it on your calculator right now, it's going to protest. It's going to blow up. It's going to say, I can't do that. Don't ask me to do that because I can't do it. Well, the calculator doesn't say that, but it's just going to give an error message. So since you can't take the log of a negative number, that means that we have to restrict the thing that you're taking the log of as to positive numbers. Okay? The quotient law, on the other hand, says if I take the log of a quotient, this is a product, first one was a product, this one is a quotient. The log of a quotient is equal to the log of the numerator minus the log of the denominator. Now, this makes sense because of what we know about product and quotient law of exponents. We know that if two things have the same base, that we can add their exponents. So that's kind of what we're saying here, because I keep saying a log is an exponent. If two things have the same base and you're dividing them, you can subtract their exponents, which is exactly what we're doing here. So that's why the laws make sense. Now, let's try to answer some questions with those laws. Write this as a single logarithm. The log base 5 of 6, oh, sorry, my laptop is just falling off the table here. The log base 5 of 6 plus the log base 5 of 8 minus the log base 5 of 16. What is that? Well, according to the product and quotient laws that you just saw, that should be equal to, first of all, it's a log base 5 because it has to be the same base of the 6 times the 8 divided by the 16. Why? Because I'm adding the two logs together, which means I can multiply these two together. And then I am subtracting this one, which means I'm dividing by that one. So that's what the law allows us to do. Well, why don't we maybe reduce this down a bit, right? This, I was trying to use a different color here. Hang on. This would be 1, this would be 2. And I can probably do this as well. So this would be 1 and this would be 3. So it means that at the end of the day, this is the log base 5 of 3. There's your single logarithm right there. No, we can evaluate that, but they didn't ask us to evaluate it. They just asked us to write as a single log. So as a single log, one log, instead of all of these different logs, it'll be log base 5 of 3. Okay? Okay, next one. The log of x plus the log of y plus the log of 3x and it's a log of y. Okay, okay. So that means that's the log of, again, I have the x being multiplied by the y being multiplied by the 3x, and then I'm dividing by the y at the bottom. And by the way, it looks like, since I'm doing that I can write that, and that's base 10, by the way. If there's no base, then it would suggest I'm dealing with a base 10 log. So I'm not going to write 10 in because it was assumed at the very beginning. So that means that I can now multiply the x times the 3x. That looks like I'm taking the, and by the way, the y's are going to cancel each other out, right? So that means that I'm taking the log of, well, x times 3x, that would be 3x squared. Okay? We know that x times x is x squared, and there was a 3 there before, so log of 3x squared. So let me ask you this then, right? I always ask this question. Can I perhaps, there's a 2 on this x here. It looks very tempting. Can I write this as 2 log of 3x? Does that look right to you? What do you say to that? Let me turn that over to the class and ask what you think. Are those two things equal? Can I apply that power law that we just learned 15 minutes ago? No, it's in the bracket you're saying? Oh, so you're saying I can't do that? I don't know. Is it because it's in the bracket? It kind of is, but okay, let me change that then. Let me say, first of all, no, this is not equal. It's not, right? It's not equal. So these two things are not equal. But let me ask you this. What if I said the log, bracket again, 3x squared? Can I now write that as equal to 2 log of 3x? Would that one be okay? What do you think about that? Can I do that? Okay, see some yeses there. Keontae, Harish, and Rachel are now saying yes. So you're saying that it's not really the bracket so much, right? It's not so much the bracket, but it's where the squared applies. The squared in this case only applies to the x. It does not apply to the 3, right? I'm only squared. In the one I'm pointing to right now, right? Hopefully you can see where I'm pointing to, right? This squared does not apply to both the 3 and the x. Down here it does. This squared does apply to both of these, right? So it's okay for me to put that 2 in the front and say it's 2 log of 3x. But in this case, the one I started off with, this is not okay. So don't do that. Don't get tempted. I know it looks tempting, but you can't do that. Would the second option be like the log of 3? That's exactly what I'm saying. The second option is, and that's what, if you look at the line above it, it's a log of 3x all squared. That's what I was saying, right? And in this case, that 2 can go in the front and be represent basically the same thing. Now, we need to go back because one of the things that we always have to do when there are variables is to state restrictions. There are certain values of x and certain values of y that are not permissible. Can you tell me what those values are? Look back at the original function. Let me point to it right here. Look back at this and tell me what values of x and tell me what values of y are restricted, right? I have to put a limitation on the values of x and y. Can you tell me what that is? X can't be equal to 0 and x can't be greater than 0. So which is it? Is it both or is it 1 or is it, well, okay, those are not quite the same thing. Ari says 1 and everything below 0. 1 and everything below 0. Well, here's the bottom line. All right, so you're kind of warm. Both of you, well, one of you actually got it right. is that x has to be positive, has to be greater than 0. It can be a decimal. You can take the log of 0.5. You can take the log of 0.001. We've done that, right? But you can't take the log of a negative number, right? You cannot take the log of negative numbers. It has to be greater than 0. And can it be 1? Well, yeah, you could find the log of 1. That's okay. Just that the log of 1 is 0, right? So it's okay to find the log of 1, but the log of 1 is 0. All right. So anything that's positive, as long as it's positive, you're good. Okay, let me see. I think I know why you brought up the 1. You don't have a base of 1. So if it was a base here, that was the variable, then we'd say that the base cannot be 1. A base of 1 doesn't make sense with logs, right? Because 1 to the power of anything is still 1. So that's why we don't use a base of 1. So there you go, folks. This question is now answered. The final answer is this. Actually, let me put this beside here. X greater than 0 and y greater than 0. This is the answer. This is not the answer because that's not the same thing. So let me make sure that nobody thinks that that's the same thing. All right. Let's try another one. Let's try to evaluate the log base 8 of 4 and the log base 8 of 16. And by the way, I'm going to do this 2 different ways. Right? And as you know with math, and I say this all the time, you can find a bunch of different ways to do the same thing, but end up with the same answer. All right? And that's what we're going to do right here. So let's see how we can do this. Evaluate. Evaluate is different from simplify, right? If we go back to the first page, this was just write as a single log. That's all this was. This one is evaluate, which means at the end of the day, I need a number. Need a number. All right, let's see if we can figure out what that number is. The log base 8 of 4 plus the log base 8 of 16, using that product law of logs, should be the log base 8 of 4 times 16. Product, right? So multiply them. So that's equal to the log base 8 of 64, which of course is 2. There's your answer. That's your answer right there. But let's go back and review something we learned yesterday, right? I did this with you yesterday, so I'm going to do this with you again today. And let's see if we can get this answer of 2. No, so that's the answer. We got the answer by just simply using the product law. But what if we decided to figure out what the log base 8 of 4 was? We'll call it x for now. And also figure out what the log base 8 of 16 was. We'll call that y for now. Obviously, because we're doing this, we can take that x if we figure it out and add that y if we figure it out, and we should still get this answer here of 2. We should. All right. Does anybody remember what's a good way for me to find the log base 8 of 4? Don't use that change of base thing we just learned, right? I know you could do this by exponential form. Okay, so let's put this in exponential form, which would be 8 to the power of x is equal to 4. That's exponential form right there. Seems much more strenuous. True. But here's the thing, Noah, right? And I want to make sure that people realize the difference between virtual school and, I don't want to say real school, because this is real school as well, and in-person learning. If this was in-person learning, I can tell you right now, and I've done this enough times for me to say this with authority, if I gave this to you on a test, you wouldn't be even near a calculator. Okay? You'd have to do this without a calculator. You'd have to find a way to do this without a calculator. And that's what I'm about to show you right now. What happens when you have to think this through, right, in a different way than using a calculator? And I want to share, when we come back, I might share a video with you that I like to share with my class. If I have time, I might show that to you. Maybe at the end of the class, I'll show that to you. So we don't have calculus for April 1st. No, I can't control that journey. Right? There's no way for me to control that. If I'm in a classroom, then I can control that. I trust you all, but the fact of the matter is that if you're on your own unsupervised, then I cannot 100% control whether you have a calculator or not. So And Bertholds, yeah, right. So let's keep going. Let's keep going. Let's finish solving this. So how did we do this again yesterday? And by the way, the same thing works on the other side, that 8 to the power of y is equal to 16, right? So those are both exponential form of this equation. So tell me now, make them have a base of 2, both sides. Okay. So how can I express 8 with a base of 2? And I want to get a little bit more involvement here. I can't have Jeremy and just a few other people taking the load here. How can I express that 8 with a base of 2? All right, so 2 to the power of 3, good. So 2 to the power of 3 to the power of x, so the x is still there. And of course, 4 is 2 to the power of 2. Everybody knows that. So what I'm going to do now is I'm going to say this is 2 to the power of 3x is equal to 2 to the power of 2. Am I going too fast here, folks? Am I going, everybody okay with that? And therefore, I don't need the base anymore. That 3x is equal to 2. And that means that x is 2 over 3. So we can fill in that information right now. This x, I'm going to take away actually, I'm just going to put this here. This is 2 over 3. We figured out what x was. All right. So let's now figure out what y is. Do the same thing over here. What base can I use? Well, we just did this a few minutes ago for 8. We said that this was 2 to the power of 3. So 2 to the power of 3 to the power of y. Is there a way for me to express the 16? What is a good way for me to express the 2? Thank you, Axa. Thank you, Emily. Thank you, Kale. And thank you, Keontae. 2 to the power of 4. So that means that 2 to the power of 3y is equal to 2 to the power of 4. I just multiplied the 3 and the y together. So therefore, 3y is equal to 4, and y is equal to 4 over 3. So what that means is that this y that we had up here, we just erase this. This y was actually equal to 4 over 3. Right? The log base 8 of 16 is 4 over 3. And by the way, I'll show you again how we justify that. But we really just have to add these two together now. Right? So 2 over 3 plus 4 over 3, well, that would be 6 over 3, which obviously is still equal to 2. So we have the same answer of 2 by this little shortcut method here, right? The log base 8 of 64 is just simply 2, or individually calculating the log base 8 of 4, the log base 8 of 16, and that gives me this fraction here of 4 over 3 and 2 over 3, which you can add together, 6 over 3, which of course is equal to 2. Now, how can I say that, and we'll get to this one down here in a minute, how can I say with such certainty that the log base 8 of 16 is actually equal to 3 over 4 over 3? And that's because 8 to the 4 over 3 means the following. I said this to you yesterday. It means the cube root of 8 raised to the power of 4. Oh, that's ugly. Let me fix that. That's hideous. Hang on, folks. Let me undo that. Make that look a little bit nicer. So I'm saying that 8 to the power of 4 over 3 is actually equal to the third root of 8, because that's the denominator here, then raised to the power of 4. The third root of 8, of course, is 2, and 2 to the power of 4 is, in fact, 16. So we're getting that 16 that we are saying the y is, because 8 to the power of 4 over 3 is, in fact, equal to 16. Okay? All right. One more, and then we'll take our break. Actually, there are two more. So we'll do one more, then we'll take our break. The log base 3 of 405 minus the log base 3 of 5. That's not hard, right? That's easy. Remember, this is a difference this time. So this is going to be the log base 3 of 405 divided by 5. Okay, 405 divided by 5. So this is the log base 3. Let's see if I can do this mentally now. 540, that's 81. And that is, of course, look at that, Jeremy. Thank you very much. Did you use a calculator for that, Jeremy, or did they do that in your head? Which one? Nope, meaning nope to which one? I said two things. So which one? How did you do that one? In your head or the calculator? No calculator. Good for you. All right. So what's the log base 3 of 81, folks? All right. That's equal to 4. Thank you, Joel. And we have time for this last one, so we'll just polish this off before the break. All right, so 2 log 5 plus a half. Whoa, okay. What do I do with this? Well, here's what we're going to do with it. That 2 log 5, right? I'm going to make that 2 log 5 into the log of 5 to the power of 2. That's the opposite of the power law. Or it's the power law applied the other way. Let me put it that way. Plus the log of 16 to the power of a half. I'm doing the same thing for both. Right? And then I'm going to say, okay, this is the log of 25 plus, what does this half mean again? I keep forgetting. I need you to help me out. What does it mean when I raise something to the power of a half? It's the square root. So it's the log of the square root of 16. So it's the log of 25 plus the log of 4, which is, one more line here, the log of 25 times 4. All right? Because remember, that's your product law at work there. Multiply them now. So that's the log of 100. And can that be evaluated? Of course it can. The log of 100, of course, is what? It's 2. Log of 100 is, in fact, 2. All right, take a break. It's 11:15. We're back in 5 minutes at 11:20. How about this one? Right as a sum or a difference. It's kind of the other way around. Last time we had sums and we had to put it as 1. Now we're going to take 1 and try to split it up into a product, into a sum. So in this case, my answer would be the log base 3 of x plus the log base 3 of y. Okay, but again, I have to have a restriction, and that restriction says that both x and y must be greater than 0. Right? So in a case where I have variables like this, I really need to state that the variables are limited in their what they represent. Okay, so x must be greater than 0, y must be greater than 0. It's a sum of those two. And by the way, I should mention, always look back to the original when you are coming up with restrictions, not at the final product, not at this thing down here. Look back at this starting point. Okay, log of 20. Well, there's more than one way to do that. Can anybody think of a way that I can write the log of 20? Anybody can think of a way that I can write the log of 20? Give me different ways that I can do that. What's the log of 20 equal to? And there's more than one way to do that. Come on, folks, help me out here. Give me a way to write the log of 20 as a sum, in other words. Add two things together, or says sum or difference, I think. Yeah, sum or difference. I don't see any hands going up here. What's going on? Can you not think of a way to? I'll do the first one then, since somebody has an answer for that. I'll do the first one. The log of 20 could be the log of 10 plus the log of 2. That's the log of 20 right there. And in fact, in this case, I could say it's 1 plus the log of 2. Why? Because the log of 10 is 1. Can you give me another way that I could write this? Any other way that I could write the log of 20? Not sure why I'm getting complete silence here. Give me another way that I could, okay, let me write this word, another option. would be what? So the log of 4 plus the log of 5? Absolutely. How about a difference? Jeremy and Harish came up with the same thing. Can I write this as a difference? There is a way I can write this as a difference. Give me a way I can write this as something minus something else. Right? Can you think of a way that I could do that? This minus that. Can nobody think of the log of, there you go, or the log of 40 minus the log of 2. So we're saying there's a whole bunch of different ways that we could write this as a sum or a difference, right? So one of them is just log of 10 plus log of 2, right? Or the other one is the log of 40 minus the log of 2. I mean, there are other ways that we could do it. Infinite possibilities. You're absolutely right about that. Okay, let me now tackle this guy right here. The log of a b squared c, right? The log of a b squared c. So give me some possibilities here. Log of ab plus bc. Interesting. Interesting. That's certainly one possibility, right? Or how about we do this? The log of a plus the log of b squared plus the log of c. Right? How about we did that? Or we could further do this as the log of a plus 2 log b plus the log of c. Right? But we still have to use the restrictions, or still have to state the restrictions. So the restrictions here would be what you expect. A has to be greater than 0. Now, some people would argue that the b does not have to be greater than 0. Why is that? Why does the b not have to be greater than 0? If you look back at the original expression, you could argue that the b is going to be squared, so it doesn't need to be positive. It could be negative and that would still work. But some people would argue that, well, when you get to this point, you're going to end up with a log of b here. I'm going to go with that. It's really only the b, the a, and the c that need to be positive. I'm going to go with that side of the argument on this one, right? That if my b was negative, that would still work, because if it, from this point of view, it would work. Well, it would work here as well. The only place it wouldn't work is when I get to this point down here. Okay? Okay, so let's get this last one on this page and then we can move on. The log of u times v over the square root of w. All right. So let's see. That will be the log of u plus the log of v. And hopefully you can tell my v's from my u's. Hopefully, right? And then minus the log of the square root of w. And yes, what Jeremy just said is true. I can write that as the log of u plus the log of v minus half of the log of w. Where does that half come from? Because that's the exponent on the w. Do you mind scrolling to the top afterwards? I can do that. But I need to write my restrictions first. The half comes from the exponent on the w, and that half can go in the front as a coefficient. So the restrictions here would be the ones that you would expect. I don't have to write the word restrictions. I'm just going to put what the restrictions are. So that u must be greater than 0, v must be greater than 0, and w must be greater than 0. Okay, so you wanted us to go back up. Does w have to be greater than 0 because it's real numbers? W have to be greater than 0. Well, yeah, not that it still has to be greater than 0 because you're taking a square root of it, aren't you? All right, and we don't, yeah, we have, don't, yeah, we're talking about real numbers here, only real numbers. All right. I don't know how far if you wanted us to scroll. Which one did you want us to look back at again, Jeremy? Which one of these did you have an interest in? Just the top. So that's the one. So right there, then you see it now. Okay. All right. I'll give you 15 seconds on that, and then we're gonna move along. Right? We're going to get to the University of Waterloo page in a second, which is where I'm going to get everybody involved. We're going to go for a wheel, and we're going to spin the wheel and call some names. I'm going to get everybody to participate at that point. All right? Or with W with an exponent of a half. Could you accept an answer with the W in the square root? Um, yeah, I don't see anything wrong with that. Yeah, I wouldn't see anything wrong with that. Many times it might be useful to have that half in the front though, right? If you're working something out, it might be useful rather than taking the as a square root, think of it as being W to the half and then putting the half in the front. Okay? Yeah, so it's acceptable. There's nothing wrong with it. No. All right. Now, how about this one? Simplify this. Now, there are two approaches to this one. One approach would be to say, how about if I simplified what I have right now? And I'm going to take that approach, right? Can this thing inside here be simplified? And I'm going to say yes to that, right? Because I can express the top, which is the square root of x, as what? Right? What's another way for me to express the top of this fraction? That's square root of x. We talked about this before, right? It's the x to the power of what? X to the power of a half. And the bottom was x to the power of 2. Right? So, what do you think I'm going to be suggesting next that we do? Rather than using product law and quotient law and all these other laws, what do you think I'm going to suggest we do right now? Right? I have the log of x to the half over x squared. What do you think I'm thinking? To read my mind. Can you subtract? Of course you can. Because one of the laws of exponents says that if I have the same base, I can subtract the exponents. It's going to be the log of a half to the power of, x to the power of a half minus 2. Does that make sense, everybody? I want to make sure it does, right? And if it does, then it means that I'm trying to find the log of x to the power of minus 3 over 2. A half minus 2, minus 3 over 2. Which means that I would end up with minus 3 over 2 log of x. Sort of. Okay. All right. I'll tell you what we'll do then, Isaac. I'm going to copy that question. I'm going to do it a different way. And we're going to end up with the same answer, but I'm going to do it a different way. I'm going to use those product and quotient laws just to make sure that this makes sense. So I'm going to come back up here. I'm going to copy that. I'm going to paste this here. Oh. And we're going to use those product and quotient laws that we learned to do this. Okay? So here we go. I'm going to call this equal to, and by the way, we didn't put restrictions on the previous page. I'll do that in a minute. The log of, that's not log, Mr. Kamak. The log of x to the power of a half over x squared. Can we agree on that, Isaac? Let's just make sure that we're good with that. That I can write that x to the square root of x as x to the half. Can I? Does that part make sense? Okay, fine. So here's what we're going to do now. I'm going to write this as the log of x to the half minus the log of x to the power of 2. Does that make sense so far? Using that quotient law that we talked about, that we can subtract those two things from each other. Does that make sense, Isaac? Perfect. So now the next step is to use that power law that we just learned in the previous class and say that's equal to a half log of x minus 2 log of x. Does that make sense? Because we just learned that in the previous class. Not just Isaac, but everybody else. Right? Does everybody follow the logic of that? It's a half times the log of x, right? Minus 2 times the log of x. Not just Isaac. Thank you, Isaac, for chiming in. But how about everybody else? Right? How does Janaya feel about that? How does Neil feel about that? Right? Do those two things make sense? Thank you, Elizabeth, and thank you, Axa, and thank you, Travis. But I'm asking about Neil, and I'm asking about okay, Neil, okay, great. But then, aren't these like terms here? Half log x minus 2 log x, right? So shouldn't I be able to put them together? It's a half of this minus 2 of that, and say this is the same thing as minus 3 over 2. A half minus 2 is minus 3 over 2 log x. How does that look to you, Isaac? Wouldn't that make sense? It's like saying a half x minus 2x, except it's a log of x this time. Do you see where I'm going with that there, Isaac? Do you see what that makes sense? And by the way, you'll notice that it's the same answer as before, right? When we go back to this page, minus 3 over 2 log x, minus 3 over 2 log x. Okay? And also, x has to be greater than 0. That's kind of hopefully understood as well, right? X has to be greater than 0. Okay, great. Thank you, Isaac. And thanks for saying that you weren't 100% clear on that, because that's important to me to know that. All right. One more on this page here. Actually, why do I have this graphic here? Oh, I remember why now. I'll show that graphic to you later on. Let's take this one here. What is all of this here stuff that I have down here? I don't even know what this is. I'm not even sure what that is. All right, we'll get to that. Let's get to this. In fact, let me put this on another page and work it through. What are you asking us to do with this? Simplify it. So I'm going to simplify this. We don't have enough room on this page here. So let's copy it. Drop a page in there and paste it. All right, this is going to be similar to the one that we just did in a manner of speaking. We're trying to simplify this. It's log of the square root of x to the power of 3 plus the log of x squared minus the log of the square root of x. Whoa. Okay. Okay. So why don't we call this thing here? Okay. Can anybody think of how we might do this? And let me get some ideas from you first. I'm trying to simplify this thing. Right? Any ideas on how I can simplify this? The log of the square root of x to the power of 3 plus the log of x squared minus the log of the square root of x. Is there a way that I can express these differently, is my question. Okay, would the first one be x to the power of a half to the power of 3? Absolutely. Change all the x's. All right. Okay, I hear what you're saying, Noah. I think we're both on the same page. So I'm going to say the log of x to the power of a half to the power of 3 plus the log of x squared minus, I'm going to do the same thing here, the log of x to the power of a half. Let me just stop and see if everybody is following me on that. That makes hopefully good sense to everybody. And then I can actually put these two together to be the log of x to the power of 3 over 2 plus the log of x squared minus the log of x to the half. So where do you think I'm going to go next with this? With all of these log x to these different exponents. What do you think I'm going to do next with that? All right? I'm going to use a power law. I'm going to take each of these exponents, put them in the front. So that's equal to 3 over 2 log of x plus 2 log of x minus half log of x. That's what I'm going to do. And all I'm going to do now is just put everything together into one big happy family. They're all log x's. They belong together, right? So that's 1.5 minus a half, which is 1, plus 2. So that would be 3 log x. Does everybody see that? Let me check in with the room on that. I want to be sure that everybody is on board with that. Nicholas, how about you? Nicholas, where's Nicholas at? Check in for me, please, Nicholas. All right. Can you repeat the last step? I sure can. All I'm doing is recognize that these are log x's. That's a log x, that's a log x, that's a log x. So I'm going to just simply combine my like terms. That's like saying 3 over 2 plus 2 minus a half of log x, right? Because those are all the coefficients. These are like terms. This is a log x, that's a log x, that's a log x. This is 1.5, 3 over 2, that is. This is 2, this is minus a half. No, it says I would add the x's and then put the 3 in the front of the end. Yes, yes, no, you're right. Yes. And Nicholas, does what I just did make sense to you as well? Nicholas, what do you say? Okay, so there's my answer, 3 log x. And that is done. You cleared it up. Okay, I cleaned it up. Okay, good for you. All right, let me go back and see what else we have over here that we haven't done yet. Oh yeah, this one needs some attention here. Let me copy this one onto a new page and talk about it. Oh, did I put the restrictions for this? I did not. I did not. So here's my answer. And of course, x has to be greater than 0. All right. So how about this one? Let me copy this one as well to a new page. We're supposed to simplify this. All right, simplify this. All right, so I'm thinking, okay, if this is a difference, can I not write this as a quotient? So the log of 2x minus 2 over x squared minus 1. Oh, that's not right. All right, shouldn't that be the same thing? Because if I'm taking a difference of 2 logs, then it's the same thing as taking the quotient of 2 logs. So should I leave that there, or is there more that I need to do? So Jeremy says I should factor. Okay, let's try to factor it. So it's the log of. Well, what is the, how would I factor the top of that? What would that be? 2 into x minus 1, okay. And how about the bottom of that? Can that be factored as well? Can anybody think of what the x squared minus 1 might factor to? Not just Jeremy, no. I'm looking at the whole class here and asking you all to try to factor that. All right, difference of squares, good. So Rachel says x into x minus 1. Close, but not quite. It's not quite. Think about that a little bit more, Rachel. You're on the right track, but not quite. Go what Noah said, it's a difference of squares. Difference of squares needs 2 brackets, right? What's inside of those brackets? It's x plus 1, x minus 1, correct. Okay, so that's an opportunity for us to simplify this, isn't it? So I can actually, like when we're doing those trig identities and we find common factors there. So I just did that. So it works out to be the log, and this is a base 10 log, by the way, of 2 over x plus 1. But what about the restrictions? What about the dreaded restrictions? Jeremy has an answer. Go ahead, Jeremy. Tell me about them. So you're saying, let me ask you this then, Jeremy, since you've volunteered. You say x has to be greater than 0. Excuse me. So you're saying if I use, for instance, let's just take an answer here of minus a half, that would be a problem? Because minus a half is less, you think it would be a problem? Okay. Well, okay, go ahead. X can't be equal to 1. Okay, all right. So is that your answer? X can't be equal to 1. Is that it, or is there more to it than that? Okay, interesting. Interesting. All right, we're going to take a little different perspective on this. I want you to look at the original. Okay, I always say to you, go back to the original. This one takes a little bit more explanation than the ones that we've done before. Because it's not just a matter of saying x has to be greater than zero, because if x was just simply, I'm just using an arbitrary value here. If x was equal to, let's say, I can't think of the value off the top of my head, but it's a little bit more than just x has to be greater than zero, because it wasn't just take the log of x. It was the log of 2x minus 2. In this case, it was the log of x squared minus 1. So here's what we're going to say. And I'll show this to you using a number line in a second. We have to satisfy two conditions, right? This first thing has to be greater than 0 that I'm pointing to here, that I'm putting a circle around right now. And this second thing also has to be greater than 0. So there are two conditions that have to be satisfied. This one is a little bit more work than the others that we've done. So 2x minus 2 must be greater than 0. And x squared minus 1 must also be greater than 0. I want you to think back to when we were solving inequalities back, I don't know, maybe in the unit 2, maybe, back then, back in the good old days. Well, back then, what we said was, to solve this, we could just solve this left-hand side like a regular linear equation, right? So I'd say that 2x must be greater than 2, and therefore x must be greater than 1 by dividing both sides by 2. Remember, I'm dividing both sides by 2, which is a positive number, so it doesn't matter. The direction of the inequality does not change. So x has to be greater than 1. Hopefully makes sense to everybody. All right? How do I solve the next one? X squared minus 1 must be greater than 0. Does anybody remember how we solved that back in the polynomial unit? All right, I want to solve an inequality, which is a quadratic. That's my clue for you. X squared minus 1 must be greater than 0. How do we solve that? Factor? Yeah, we could factor. We could factor x plus 1, x minus 1. We could factor that greater than 0. But then what? Where do we go next? Graphing it. I like that, Harish. I like that a lot. Right, we know our two zeros are at plus and minus 1. And we know that this thing opens up. So here's my rough graph right there. Oh, actually connected with the 2 points this time. So if I now asked you where this is greater than 0, how would you answer that question? That's what I need to ask you, right? Where is this picture greater than 0, right? So x must be less than minus 1. And x must be greater than 1. Can we all agree on that? Does that make sense to everybody? Okay. Now I have to satisfy both of these. I can't just satisfy one side. I have to satisfy both sides of this, right? So for me to have peace in the land, right? For these two sides to get along, right? If we want there to be harmony in math land, then I have to make sure that this thing here is positive, right? Can't be less than 0. And this thing here is also positive, right? So for me to have both sides of the fence say, you know what, we can share common ground. Look at what the first side said. I'm happy when x is greater than 1. This one says, I can be happy when x is greater than 1 or x is less than minus 1. Where do they have common ground? Where is it that they're both in agreement? Can anybody answer that question? Where is it that they can both sign the treaty and say, you know what, even though we're not quite the same, there is some part that we can both agree on? And Keontae and Harish are both right. So the restriction here, right? Now remember, they both have to be on the same page now, right? They both you have to satisfy both conditions. But here's the problem, right? If you have, okay, so here's a problem. Even though I'm trying to make sure, that we can see. Okay, let me. I have a number line on one of these pages here. So let me get to the number line. Where's my number line? Here's my number line, right? So I'm going to use this number line. And oh, by the way, I have a graph of this function as well. I think that's what I have on this page here. Where was that graph that I had on one of these pages? It was at the bottom of one of these pages. Was it this page? There it is. Okay. This is the graph of the red line is showing. In fact, I can put this on Desmos as well. This is the graph of the red line, this one here, the graph of log of 2x minus 2 minus the log of x squared minus 1. What you notice is that the only part of the graph that's showing up is the part where x is greater than 1. There's nothing on the other side over here. Right? That's what this graph is basically showing you. This graph is, whereas the graph of the log of 2 over x minus 1 actually goes straight through here. So this graph wouldn't, the final graph that we got, the final equation that we got, I'll show you, was this, 2 over x plus 1. But if we just graph that, that graph would be all over the place. That graph would be all up to here. But then if we simply go back and say, what I'm really looking for is a graph of 2x minus 2 minus log of x squared minus 1, which is this red line, that graph actually just stops right here. It means only one condition makes everybody happy, and that's where x has to be greater than 1. So what we're saying is that the restriction here for this, where they are in agreement, is where x is greater than 1. That's where they have common ground. That's where everybody is happy. I'm going to do one more like this, and then we're going to go to the University of Waterloo, and then we're all going to participate at that point. I have one more like that. You can find that quickly here. That's this one here. Yeah, okay. There's another one down here. We'll just do this one. We'll just do this one. I mean, we'll do both. We'll do both. All right. The log of x squared plus 7x plus 12. So this thing is a little bit more technical when you get to stuff like this. The log of x squared plus 7x plus 12 minus the log of x squared minus 9. All right. So let's first of all write that as the log of the x squared plus 7x plus 12 divided by x squared minus 9. I didn't use a number line before because everybody was fairly, everybody was able to see the answer fairly easily. But how about this one? Well, I think we'll definitely use a number line on this one. Let's put a number line down here a bit. So I'm sure you understand that I'm going to factor the top of this and the bottom of this. So that's equal to the log of. Can anybody tell me how to factor the top, please? I need some help with factoring the top. What is that? How do I factor the top of that expression? X squared plus 7x plus 12. What is that, folks? Help me out here. Hello, where is everybody? X plus 3x plus 4. Good. And of course, the bottom is also a difference of 3. Yes, Harish, I'm sorry. I think you got that one wrong this time. Never mind. That's okay. The bottom of this is x plus 3, x minus 3. First of all, let's agree on that. Okay, is everybody okay with the factoring at least that part of it? All right. Rachel, how about you? Rachel, let me just check in with you on that. Rachel, where are you? Okay, perfect. And of course, you know that we can just kind of do this. So what we're left with is this. It's just simply the log of x plus 4 over x minus 3. So, okay, let's try to look at the domain of this thing where this is greater than 0, and so the top and the bottom where this is greater than 0. Let me maybe put this on another page. Let me cut this and put this somewhere. So maybe we'll try this one as well. We'll see. We may or may not get to this one. Let's get back to what we're working on now. So the log of x plus 4 over x minus 3. But remember, this thing has to be positive and this thing has to be positive, right? That's the condition that is going to make everybody happy. So what I'm going to do is I'm going to go ahead and I'm going to draw both of these functions on a graph. Two different graphs, by the way. The first one is the x plus 3, x plus 4. So that would mean that minus 4 and minus 3. Graph should look something like that. And then the second one, so minus 3, positive 3, that graph should look something like this. Hopefully everybody agrees with me on that. X plus 3, x plus 4 has two zeros at minus 3 and minus 4. Those are my graphs right there. So what I'm going to do now is I'm going to put these two on a number line. I'm going to ask the question, where is everybody happy? Where is there peace in the land? Where is it that everybody can say, yeah, we can sign off on this because this is where everybody is okay with this. In the first case, for me to be greater than 0, I'm going to use different colors for this now. I have to be somewhere to the left of this and somewhere to the right of this. The second guy comes along and says, okay, for me to be happy, I have to be somewhere to the right of this or somewhere to the left of this. All right, that's what we're saying. Everybody okay with that so far? This one's a little bit more complicated. That's why I think a number line really helps out here. All right, so if I was represented as I just did on the number line, can you tell me what my restrictions are this time? Right? Look at my number line. Where is there peace in the land? Where is it that they can sit down at a table together and say, you know what? Let's agree that as long as this condition exists, we're both happy. Can everybody see based on the number line? Okay. So Rachel has it exactly right. And so does Jeremy. Harish, you have half of the answer. Right? The answer is that x has to be greater than, what is it now? Greater than 3, or x has to be less than minus 4. Right? So you see what I'm saying, Harish? Both of those things have to be true. I have to be less than minus 4, or I have to be greater than 3. Harish, is that okay with you? Do you see that? Okay. And again, I think the number line really, really helps when you're doing this. Right? That's how I, because I'm a visual person, that's how I sort of put that together. All right, so there's my answer for that question. If you were to draw this, what you notice is that the graph would only exist when you're greater than 3 or when you're less than minus 4. Yeah, this is the simplified version, right? This here, and I'll circle it, that's the simplified version of the function, right? So that was what, this would be what the easiest way to work with. But the original function would have these restrictions. X is greater than 3, x has to be less than minus 4. All right, we'll do one more, and then we'll stop. So we just did, we'll just do this last one here. And then we're going to go to the University of Waterloo. All right. So this one, similar to the one we just did. But now we're going to say the log of, I don't know why I'm using green. Can we just factor it right away? What's x squared minus 7x plus 12? What does that work out to be as a factor? The bottom, I can just put that in for you right now. X plus 2, x minus 2. All right. So x minus 4, x minus 3. Okay. Okay. And I agree with that, by the way, Jeremiah. And hopefully everybody else is okay with that. No, without me having to draw the number line, I hope we're at the stage where we don't need to draw this every single time. I'm going to put in those regions that are satisfied by this top being greater than 0 and the bottom being greater than 0. All right? Okay, work with me on this now. I'm going to say that for the top, I'm working on the top right now, it's plus 4 and plus 3. So I'm going to say it's going to be this way, and it's going to be this way, right? That's where the top is happy. The bottom, on the other hand, says for me to be happy, I'll go to green now, down here, you need to be either here or here, right? So put that together for me now, folks, right? What is the actual restriction if we're looking at the original function, right? Look and see if you can tell me what that is. Go back to the original function and tell me what you think that restriction is going to be. All right, I'm going to give you a few minutes to look that over. And I want everybody to have a chance to answer the question. So I know that there are some people would answer right away, but some people might need a little bit more time. So I need you to think that through and then tell me what you're coming up with. Okay, so let's see what's going on in the chat now. Let's see what's going on in the chat here. Let's come back to the chat. Okay, so you're saying that, all right, I'm seeing a whole bunch of different answers here. Let me go back. Jeremy is saying, so x is less than 2 or between 2 and 3 or x is greater than 4. Rachel says x is less than minus 2 and x is greater than 4. And Jeremy looks like he's having second thoughts. So I'm not sure anymore what's going on. I'm not sure. So Rachel and Jeremy don't seem to be on the same page. I stand by, you stand by your answer. That's interesting. Rachel, do you think I got the same as Rachel? Interesting. All right. So Jeremy and Rachel cannot seem to, they can't sign off on this at all because they're not. So let's say Jeremy represents the numerator and Rachel represents the denominator. I'm sorry about saying my answer immediately. That's okay. Got the same as Rachel. So Harish is at least agreeing with. So Rachel at least has an ally at this point in time. How do other people feel? I'll show you the graph in a minute. I just drew the graph a while ago. How do other people feel? Look at those number lines. Again, you're looking for overlap, right? You're looking for where can we both sit down and say, yes, we share this territory. We're okay. We can both coexist right here, right? I'm it's just funny. Sorry, I'm not laughing at you folks. I'm just having a good time doing what I love to do, which is to teach you guys. All right. Uh, Harish is switching lanes here. He's saying, no, I'm going to come off of the Rachel lane. I'm going to jump into the Jeremy lane. Folks, who is right? Who is wrong? Okay, so Sharisa is gonna look. We got initially it was more people in the Rachel lane, and now people are beginning to think, I'm not so sure anymore. I might want to go into the Jeremy lane. All right. I still want to hear from some other people, though. Seriously, I have the graph ready to show you, but I want to hear from other people first before I show you the graph. What do you think is the final domain of this function, which means where does the graph actually exist is what we're trying to figure out here, right? And I've only heard from 3 people so far, Jeremy, Harish, and Sharisa. I think those are the only 3 people, yes. And Rachel, of course. Oh, Rachel who had an answer already. Sorry. I certainly want to make sure everybody is in on this. Right? Anybody have another opinion on this? I'll share the graph with you in a minute. And then when we look at the graph, that would be the final sort of, that would be the deciding factor when we look at the graph. Come on, folks. Keontae, I can see why Jeremy is right. All right, I'm going to share the graph with you now. So I'm going to stop sharing this, and I'm going to share the graph with you. So let's see what the graph says. I'm going to go to my Desmos graph right now. Remember what Jeremy said, remember what Rachel said, okay? Just remember what those 2 people said, and then let's see what the graph says. Okay, so here's the graph, right? This, and you can look at the equation, you can see log of x squared minus 7x plus 12 minus the log of x squared minus 4. It looks like the graph exists. So now that you've seen the equation, I'm going to minimize this so you can see the graph more clearly. It looks like the graph exists anywhere to the left of 2. There's a part of the graph, though, that seems to be somewhere between 2 and 3. There's a little part right there. And then it skips over, and then it's anything to the right of 4. Everybody see what's going on here? Let me say it again. Anything to the left of minus 2 is good. There's a big gap here, nothing going on here. Anything between 2 and 3 is good. Another big gap, another big gap, another gap right here. Anything greater than 4 is also good. Let me stop sharing. And by the way, let me show you the equation again. It's the same equation that we're working with. I didn't change anything. I didn't put the simplified version of it, though. Simplified version would not be the same. Simplified version would probably not have the same restrictions, but the original version absolutely has those restrictions. Okay? So, who was right and who wasn't close, but not quite there? What do you say, folks? Who was right all along? It was Jeremy, by the way, as you can see. So the answer, based on the graph, is that your restriction is that x must be less than minus 2. You saw that from the graph. Or, and we can use a union sign to do this, by the way. You can see why Jeremy is right, Keontae said a few minutes ago. Anywhere between 2 and 3. So actually, you know what I'm going to use? I'm going to use I find it easier to use the brackets. I'm going to use the brackets instead. I'm going to use the brackets instead. So here is my answer using brackets. I'll go back to black actually. Minus infinity up to minus 2 union with 2 to 3 union with 4 to infinity. You mind sharing your smart board? Oh, sorry. I'm so sorry. I forgot that I wasn't sharing my smart board at that point. I am so sorry. Let me go back to that. I'm still sharing. Yeah. Yeah, I just realized that I was still sharing the other screen with you. So let me go back to the smart board here now. All right, so we're back to the smart board. Yeah, I think everybody can see my smart board now. All right. Visible to others. Do you mind sharing? Okay, so you can hopefully see that this is what I have as my answer. Minus infinity to minus 2, 2 to 3, because there's an overlap right there, right? You can probably see the overlap between the 2 and the 3. In fact, let me emphasize that a bit here. So between here and here, there's overlap here, between 2 and 3. Then when you get beyond 4, there's overlap again. Okay? All right, so Riddy is on board with that. Jeremy, yes, you are right. And Rachel was close, but she just missed the part between 2 and 3. That's the only part that Rachel didn't get, but everything else was good. All right. Can we now move along to, is everybody clear on that? I don't think I need to do any more of those. You can try some of that kind of stuff on your own, but that's the most technical part of doing this, when you have to figure out where there is overlap between various sections. When you have to satisfy everybody's conditions, you look at where you have common ground. This comes up in other areas of math as well, by the way, other areas of logic, and hopefully that makes sense to you. Okay, so what I'm going to do now is I'm going to stop recording and stop sharing.